Now, so coupling function formulation is the topic, and now we will consider a general reaction, okay, and a general reaction, but a one step reaction, because it is, though it can be applied to multi step reaction, it is easy to understand in terms of a overall one step reaction. So, a general one step overall reaction, is nothing but this one, I is equal to 1 to n. If you remember our formulation from the kinetics class, mi goes to summation I is equal to 1 to n nu I double dashed times mi, okay. And then the species independent reaction rate, which was omega, is given by the species consumption rate Wi divided by capital Wi, which is the molecular weight of the species, nu I double dash minus nu I dashed. Now, if you have any confusion with this formulation, you can just go back to the kinetics theory, the chemical kinetics class, and just take a look and get refreshed. Whereas this guy is nothing but b t to the power of alpha exponential of minus Ea by r0 t. This part is the reaction rate constant k times the law of mass action, that is, depends on the continued product of the species concentration raised to their stoichiometric exponent Cj nu j dashed. Okay. Now, if we consider the distinct specific formulation, okay, and which was and get the species conservation equation, that was, this is Cpi the distinct specificate, whereas Dij is equal to d, that was the statement of the species distinct specificate formulation. So, this was the species conservation equation was dou rho I dou t plus divergence of rho v vector species consumption or production rate, and that becomes, when you apply this onto here, this is the left hand side. So, this is once again convection term, this is the species diffusion term. You see the characteristic diffusivity comes to rho d is equal to the molecular weight of the species I times nu I double dash minus nu I dashed times the species independent reaction rate omega. Now what we can do is that we can define a stoichiometrically weighted mass fraction. Now, we will use some non-dimensional parameters, because these non-dimensional parameters, as you see, will make our life much simpler in terms of the analysis. It will immediately it will look a little complicated, and it will not be clear why we are actually doing this kind of non-dimensionalization, but later you will see that when you do this kind of a non-dimensionalization, the equations becomes very simple and solution just will involve one or two steps. So, the equations become much more simpler to solve, and of course, it becomes much more insightful. So, yi tilde we define is the non-dimensional stoichiometrically weighted mass fraction is given by 1 by sigma in yi divided by yn at boundary. What is ynb? I will define sigma n immediately, but before that, ynb is the species mass fraction of an nth species, which is a reference species at a boundary of my domain. What I'll come to this when I will consider a specific example, which is at the domain boundaries, where this thing is essentially known and fixed. So, that is why we define it at the boundaries. Of course, you need to know the boundary conditions to solve it. So, it must be known at the boundaries. Okay. So, whereas sigma in is equal to molecular weight times the stoichiometric coefficient difference divided by the same for the nth species, which is the reference species. Okay. So, this is the thing. So, now when you put this into this, what we get is nothing but we can write in terms of an operator d rho dt. This is the operator actually, not the full thing. Rho v, there is a convection term, plus operating on a quantity, any quantities, okay, and this can be actually operating on y I tilde, and that is equal to w n, whereas. So, this is what we have obtained from the species conservation equation. Okay. We took the species conservation equation in the distinct specificate formulation. We applied this non-dimensionalization of y I tilde is nothing but y I by y n at the boundaries, which is known, divided by 1 by sigma I n. Sigma I n is nothing but w I divided by nu I double dash minus nu I dashed divided by w n nu n double dash minus nu n dashed. Okay. And then if we apply these two things in the distinct specificate formulation in the species conservation equation, we arrive at this thing. Okay. So, this is in an operator form, which we can write it as this L d y I tilde is nothing but w n. Of course, because of the coefficients in the front, now w n changes, and w n is nothing but this thing. Okay. Now, this was the species independent reaction rate, and all these things arises because of the non-dimensionalization. You should, I mean, it does not look at all complicated. You should just take the equation and just do these things yourself, and then it will become as clear as possible. It will become very clear. But then you see that now we can write this full thing. The thing is that whereas this is the our operator L d, this bracket, whatever is in the bracket, which is operating on essentially this guy, this y I tilde, and that is equal to w n, so that we can write this form essentially. So, now we can, because this is true for any species w I. Now, the advantage that you see here is that we have written this operator, this d rho, the operator is d rho partial rho t operating on y I plus the divergence of rho v vector minus rho d divergence operating on y I is equal to w n. Now, the advantage is that on the right hand side you do not have a species, this species specific the species specific reaction rate, in the sense that you have a w n which is only written in terms of the reference species. Okay. It is not in terms of the ith species. So, this on the while on the L y on the left hand side you have an L d y I, it is on the right hand side we have a basically a source term which is not dependent on y I ith species as such. Okay. It is dependent implicitly through this thing, but not explicitly. But so what I can do is that I can write another equation L d y j tilde, and that is also equal to w n, and then we can just subtract. Now, because all these differentials that we see are commutative with respect to linear operations, that is addition and subtraction, I can write L d y I tilde minus y j tilde is equal to 0, because these are just, when you subtract them, this becomes equal to 0. So, now we can basically we have arrived at a conserved scalar, which is nothing but this quantity beta, I can say that is beta I j, okay, which is y I tilde minus y j tilde, and this operator L d is equal to 0. So, by this you have basically got rid of the reaction rate term, right. So, that is the advantage here, all right. So, to just summarize what you have done is that we have basically arrived at this, we took this was the species conservation equation for constant d, that is a specific heat constant specific heat, and then we considered this one step reaction and this was our species independent reaction rate. And what we saw here is that when we write it in terms of this, we can write this in terms of omega, and then of course this is in a slightly different form, and then similarly for j we can write it as like also in omega, and then when you subtract these two things it becomes 0. Of course this here we have not done the non-dimensionalization, but if you do the non-dimensionalization, it's actually the same thing. Okay. So by this we have actually obtained that this Bij becomes essentially a conserved scalar, and for the reacting flow, so L, this conserved scalar with this operator L Bij is equal to 0. Okay. Now consequently the fundamental variable is not yi but a stoichiometrically weighted variable this. So that is the trick essentially here which we have done. It was the same thing when we have did it in the non-dimensionalization, which you can also do without this non-dimensionalization, but it has to be weighted with a stoichiometric variable, and that is what causes this removes this this right hand side on this one. Also, as I said, that we can also define a non-dimensional function like this, and also we can define a beta ij to be like yi tilde minus yi tilde. That is what we just shown here. Okay. So these two are essentially the same things, and we can do it in a both way. And now the thing is that but this we got rid for the species essentially. Now for the energy conservation, you can actually do a similar thing. Of course the energy equation is a little more complex. This is the sensible energy equation where we have a two source terms, one from dp dt and from this thing, and now we can again define another non-dimensional quantity, that is hs tilde, which is equal to hs divided by ynb divided by qcn, or t tilde is equal to cpt divided by this thing. Now ynb is once again the species mass fraction of a reference species known at the boundaries, and what is QCN? QCN is essentially a stoichiometrically weighted heat release rate. Okay. So this is what this thing is, and then if you non-dimensionalize p tilde also as rho and t tilde, then we can define another operator operating on a non-dimensional hs tilde, and that is given by this. Okay. So if you add the results of A and D, that is the previous thing that we have obtained, that is this contains once again Wn. So if you see that this L, that is LD of yi tilde is equal to Wn, and here from this we get this L of hs tilde is equal to this transient term 1 minus 1 by gamma dp tilde dt minus Wn. Okay. Now if we add these two things, what we find is that these two are actually essentially the same thing. So we can write it as the operator L. So yi plus okay. And if it is a steady state which is such that dpt is equal to 0, so then we have this whole thing becomes is equal to 0, and then you have we can define this full thing as beta I, and then you have L of beta I is equal to 0. Okay. So this is another when you couple, we can using this coupling functions, you can essentially couple between your stoichiometrically weighted or non-dimensionalized enthalpy, sensible enthalpy, and your non-dimensionalized species mass fraction, or stoichiometrically weighted species mass fraction. Of course species mass fraction itself is a non-dimensional quantity, but with this you can when you stoichiometrically weighted, you can essentially sum these two to get rid of the Wn term, that is the source term. And so as we have seen that this is what we did in a chemically reacting flows and diffuse system governed by n+1 equations. You have L of yi tilde is equal to Wn, L of hs tilde is equal to minus of Wn if dpdt is equal to 0, and this can be alternatively described as L of beta I, that is if we sum these two things yi plus hs tilde is equal to 0 and or LHS tilde is equal to Wn. So this of course the thing to note here is that if you have n species, of course you have n governing equations and you have one hs tilde, right. So you have n plus 1 equations actually. So you can combine between all of this. With each species you can sum up this hs and then you can get rid of the species reaction rate term, but then you will still be left with this one, that is L of hs is equal to minus Wn, and it should be there because you cannot really, if you are solving for a combustion system, you cannot really get rid of the reaction rate. It is not physically not possible. So you still keep it there, and this will be used to basically obtain the hs tilde. Okay. So with this you can simplify the equation by we can get rid of essentially the source term and this coupled. So each of these beta i's can be solved independently, and then after you have solved, you solve for this, and then you get the complete information about the yi's and the hs tildes. Okay. So this is what we want to say, that n equations can be solved for conserved scalars of beta I, but the chemical information is essentially then contains in the n plus 1th equation, and then LHS is equal to minus n, which is solved last. Now of course, so the key assumption here is that we have to include that that the diffusivity is equal for all the species. That is the this was the distinct specificate specificate assumption, which meant that diffusivities are equal, and if the diffusivities are not equal, we could not have solved in this manner. So that is very important. There are other formulations in which so the problem is that, as you see, that this coupling function formulation requires equal diffusivity or equal unity Lewis number, or essentially unity Lewis number, and there is a local coupling function formulation which we will essentially which means that the local coupling formulation which will show which holds in a very local region in space, which can basically work for different diffusivities and non-unity Lewis numbers. So we will do that. Okay, and we will do that analysis, and because that is revealing in terms of how basically species diffusion affects this coupling functions. Now that is also important because in combustion systems this unity Lewis number assumption is not a very good assumption, and there are various key processes like instabilities in flames. This is not the thermoacoustic instabilities, but other instabilities like diffusion thermal instability, etc., which happens only because when the Lewis number is below certain region, below certain value, that is when it is less than unity, etc. So it is important to understand the concept of non-unity Lewis numbers and have coupling function formulations for non-unity Lewis numbers. And the another thing that will come out of is that this will give you the idea of the local coupling function formulations. So that is what we shall proceed into now, and we'll do the local coupling function formulations, and that we will do the derivations for that. So the local coupling function formulations, the need arises. This is the local formulation. Okay. Now the local coupling function formulation, the need arises because, as we have seen that in the previous case, the restrictive assumption for arriving at the coupling function formulation was that the diffusivities has to be always all equal. The dIjs is equal to d, and also Lewis number is equal to 1, right. So that was a restrictive assumption. So what we will do now is that we will do it only in terms of locally, where we will essentially neglect convection, neglect the Convection in the sense that the idea is that we will separate the flow into this, where the combustion is happening, into two parts, right. So suppose this is a pipe or this is a combustor in which combustion is happening in this manner, in this part. So this is your flame, right. So we will say, what we will say is that all these regions, all omega is, that is your species production rate or the species generation reaction rate, etc., species production rate or species consumption rate or the species independent reaction rate, these are all 0 here. So only part these are is not equal to 0 in these regions. Okay. So we will have when this is equal to 0, we do not need to bother about the source term essentially. So it is identical equal to 0, right. So in these regions, why do we need even a coupling function when we know that the reaction rate is 0? We only need to bother about the source term when we know that there is a flame and then it is not equal to 0. So we will only apply the coupling function in this sort of this thin regions. Okay. But in this sort of thin regions, the most important thing is that you see this because of the large activation energy, the regions are actually very thin, and the flame essentially is very thin, and when the flame is thin, the temperature rises very sharply in a small amount of in a small region, right. So it is a very compact region, and so what we can do is that we can apply the local coupling function, the coupling function formulation only in this part of the regions and not in these parts, because there the omega is this reaction rate is 0 itself. And what we will assume is that because the temperature rises in a very short region, so if you plot the temperature here in a, and this is the temperature. So if you plot, this is your temperature axis and this is the x axis. So you will see that the temperature rises very sharply like this, right. So this is a very sharp gradient that you see here. So when you have a very sharp gradient, your higher derivatives will become important. As a result, the diffusion process become important, which is because it appears as a second derivative inside your governing equations, whereas your first derivatives, which is like convection, that is becomes less important. So we will neglect convection in this region and we will only consider diffusion. So that is the essence of the local coupling function formulation. So the local coupling function formulation essentially we can apply it because flame is compact because of the large activation energy, and then we can do it. So we will consider now this distinct diffusivity formulation, okay, where dou rho partial rho dou t density Hs. If you remember the distinct diffusivity formulation, this was the generic formulation plus divergence of rho v vector Hs minus lambda by Cp gradient of Hs is equal to dP dt pressure term, transient pressure term, minus summation I is equal to 1 to n Hi 0 Wi. This was the heat release rate term, very important. So we consider steady state. So this is equal to 0, this is equal to 0, okay. And also we neglect convection because we consider higher derivatives. Of course, you see that this term has two, this is a second derivative, this is only first derivative, so you neglect here, and this is only within the flame region, okay. So it is not valid over the entire flow, it is only in the flame region, we neglect this. So the equation that we get is essentially this one. Okay. So setting all these transient terms to be equal to 0, transient terms to be equal to 0, sorry for that. So setting all these transient terms equal to 0 and setting convection to be equal to 0, because only we are interested now in the coupling function formulation inside the flame. Outside the flame there is no need for coupling function formulation because reaction rate is itself 0, and so we do not need this coupling. So only within the flame we neglect essentially the convection, and this is becomes our equation. That is, it is a balance between your gradient of second derivative of essentially the Hs, that is the conduction, and reaction. Okay. Now similarly for the species governing equation in the distinct diffusivity formulation, this was the equation rho yi plus divergence of, so this is the species, this is the sensible enthalpy. This is the species equation. Once again, transient term, convection term, diffusion term is equal to species production or consumption rate for I is equal to 1, 2 up to n. Of course, we neglect this because it is we consider steady state, we can neglect this because we consider convection to be not important. So, we arrive at this quantity. Okay. So, now with the same non-dimensionalization, okay, that is Hs is equal to Hs tilde is equal to Hs divided by Qc is equal to your Hs divided by Ynb divided by times Qcn, that is this was the normalization. If you remember, Hs tilde is equal to Hs, okay, by Yn. This is important because this will be required in our next analysis of a flame also, QCA, non-premix flame as such. So, this is the normalization, and okay, and if you remember, Yi tilde is equal to Yi divided by Yn times 1 by sigma this is Ynb. This was 1 by sigma In, whereas sigma In was given by Wi nu I double dash minus nu I dashed divided by Wn nu n double dashed minus nu n dashed. Okay. Now, if we apply this normalization, I will just erase this of normalizations. If we apply these normalizations in this equation and this normalization in this equation, okay, okay, what you get essentially is, I will just write it down. You get, and if you assume that this is spatially non-uniform, it does not vary in space. Okay. Similarly, this is constant in space, does not change in space. Okay. So, that it can take this out of the gradient and you can take this out of the gradient. You get Laplacian of sensible enthalpy, non-dimensionalized sensible enthalpy is equal to Cp by lambda times Wn. Remember that form of Wn which we discussed, and del square Yi by Lewis number of I species is equal to minus Cp by lambda Wn. So, and whereas Lewis number of ith species is nothing but lambda by rho Cp times di. Okay. So, as you see that these and these are essentially same things with just with a minus sign. So, we can just add these two things up and define a new quantity beta I to be equal to beta I is essentially Hs tilde, sorry, Hs is here, it is a superscript not a subscript, plus, sorry, this is tilde Yi tilde by Lewis number of I, and this gives del square beta I to be equal to 0, right. Laplace equation, right. So, you see that with this coupling function formulation and this normalization, that is a part of this normalization. So, you have converted this very complicated set of coupled equations. Okay. Of course, there has been assumptions that its transient term is 0, convection is 0, but even then you have converted this whole thing into this very simple Laplace's equation, right. whereas del square beta I equal to 0 and beta I is essentially 0 conserved scalar. So, I strongly encourage that you do this derivation yourself. You can take a look into the book also. It is basically I followed from Professor Law's book, CK Law in Combustion Physics from Cambridge University Press. So, but this will give you a very strong sense of the different balance of the species and the enthalpy that is happening. It might look little bit complicated in at first glance, but this is very important because it gives you a full sense of how these things how basically the you can form a conserved scalar even from non-conserved quantities which are individually not conserved. So, we can add them up and then when you add them up carefully and with proper weighting, so you can create conserved quantities. The reason is very simple, fundamental. The reason is that when you consider as reaction, consumption of one means production of another, right. So, it is that property that you have utilized, and these things are all related. It is not that those species are essentially independent, neither the enthalpy is essentially independent, right. So, because of utilizing that, we have arrived at this from a very complicated set of equations. So, these were the two equations. First we essentially got from the full set of equations, if you remember from the full set we simplified it into this form, which is the distinct diffusivity form, and from that we arrived at this simplified form. We also considered the so this was the full complicated form of the sensible enthalpy equation. From that, by applying the fact that your transient term is 0 and transient term is 0, we applied at we came at and we considered convection to be 0 because inside a flame only the steep gradients matter, so the diffusion terms matter. So, essentially the flame is a balance between your diffusion and your reaction, thermal diffusion and heat release rate, whereas and then we consider the species equation, where we basically considered the transient term to be 0, and then the convection term to be 0, and once again it become a balance between species diffusion and the species consumption or production, and then we normalize this enthalpy and normalize the species mass fraction, and then we arrived at this coupling function, which is beta I is equal to Hs tilde plus yi tilde by Lewis number of the ith species, and then we arrived at this Laplace equation, which is a beautiful simplification from these complicated forms. So, ultimately we arrived at this del square beta I equal to 0. Okay. And this is a very important thing that we have done, and then in the next class what we will do is that we will utilize this to arrive at to solve for basically the non-premix flames. So, this much for the governing equations, that is so if you remember we used what we have done in this class of in these two couple of or these 3-4 classes of governing equations is that we have considered the Reynolds transport theorem to convert the conservation laws from a system to a system that is a packet of fluid moving in space to a control volume through which the packet is moving, and then we arrived at laws for essentially we have arrived at laws for mass conservation, continuity equation, momentum conservation, species conservation and energy conservation. And then we have arrived at different terms, we have arrived at constitutive relations which can close these equations, and then we have applied different kind of simplifications from so that we can arrive at useful forms of these equations, and these useful forms we have again further simplified for distinct specific formulation, distinct diffusivity formulation, and then we landed up in a problem because we found that the species equation and the momentum and the energy equation was coupled. The momentum equation did not come, we did not explicitly consider because we found that in combustion your pressure is mostly constant, so we do not need to bother about the momentum equations as such. Species is constant in space, of course the density changes and the velocity changes, but main equations that we need to consider is the is essentially the species and the sensible enthalpy equation. We also arrived at the sensible enthalpy equation by considering the internal energy equation and then converting the internal energy equation to specific enthalpy equation, the total specific enthalpy equation, and then from the specific enthalpy we subtracted the enthalpy of formation to arrive at the sensible enthalpy equation, and then from the sensible enthalpy equation we arrived at further simplifications using the distinct diffusivity of the distinct specificate, and then we removed the transient terms, and then we considered this then we also arrived at a generic coupling functions when when we consider that that the diffusivities are equal. So, when then we can apply it at generic coupling functions for generalized equations when the diffusivities were constant, were essentially same. And then if we also argued that in some cases diffusivities may not be same. So, then we arrived at the local coupling function formulation, and for that we argued that the for most part of the flow when there is no flame, we do not need to bother about the species, we do not need to bother by the fact that the reaction rate couples the species or the product the omega I, that is the species production rate or the consumption rate, couples the species mass fraction equation with the energy equation, that is a sensible enthalpy equation. We do not need to bother about this because there is no flame. So, that becomes active only inside a flame, right. So, at that parts we can simply set omega I or the Wi to be omega or Wi is to be essentially equal to 0, but inside a flame what we do is that where we cannot set this to be equal to 0 because that is where the species is being produced or species is being consumed. What we do is that we argue for the fact that because activation energy is large, your flame is actually a very thin region, occupies a very thin region in space, and if it is contained in a very thin if it is the flame is very thin, that is its thickness is very thin, it occupies a very small volume and it is a very thin structure. So, that means which is an artifact of the large activation energy of the combustion reactions. So, but if it is a thin structure, it means that the temperature or the species gradients, temperature or species gradients are very high there. So, temperature and species change very rapidly inside the flame, as a result of which it is only the diffusion process that matter and convection process does not matter as much. So, we neglected convection, we considered steady state and we arrived at the simplified equations and this simplified equations for the sensible enthalpy, simplified equation for species, and from that again we applied this non-dimensionalization of sensible enthalpy, non-dimensionalization of species, and arrived at this simplified Laplace equation for the coupling function beta I. So, that is in a summary what we have done, and then we will please remember this coupling function, please note it down, derive these things which will give you immense confidence in how the combustion governing equations work and how different parameters work among themselves. I strongly suggest you do the derivations on yourself, and then once you are ready we will come and discuss about non-premix flames using these coupling functions. So, thank you very much.